Okay, we are live. It is May 28th, 2015, 11 o'clock Pacific, and this is Deep Hangops. Today we are going to be talking about Deep Engine. We actually have a presentation from Mike Skubitz, and after that, so feel free to ask any questions while that's going on. Really want to kind of see where things are and kind of get a feel for this. And then after that, we'll be talking about what does it mean to be a DBA to you? What are your expectations of being a DBA? And also kind of start to dive into a little bit of stuff about automation and things that you automate in your role. So without further ado, let's go ahead and do a quick round of introductions. My name is Jeff Anderson. I'm a database administrator at Box. Mike, do you want to go ahead?
Sure. I'm Mike Skubitz. I'm the Vice President of Product Management at Deep Information Sciences.
Okay. Morgan?
Morgan Tucker, MySQL Community Manager at Oracle.
And Phil?
I'm Phil Hildebrand. I'm a DBA at Moz.
Okay. Shlomi?
I'm Shlomi Noach. I'm a system engineer at Booking.com.
And Sylvia?
Hi, I'm Sylvia. I am the DBA at SendGrid.
And Tim?
Tim Callahan, independent benchmarker and MySQL user now.
Okay. All right. So yeah, like I said, today we're going to get started with talk from Mike Skubitz about Deep Engine, and actually just go ahead and take it away, Mike. And I guess we'll just ask questions as you go.
Sure, that'd be great. Let's see if I can get my screen to share. Let me know when you guys can see this. So while I'm attempting to share this, let me give you a background. So Deep's been around for about 4 years. Initial product development started about 4 years ago. And we're trying to solve the problem of really massive scale-up in the relational database world. And along the way, we kind of ran into what we thought were some fundamental problems and came up with some unique solutions that we think allow us to bring scale to a new plateau, for lack of a better term. Can you guys see the screen now?
Yep, looks good.
Awesome. So, from a backstory perspective, our focus here was trying to maximize scale up of database nodes, with the theory being that the scale out would be handled at the kind of at the platform layer. So, from that perspective, we tried to figure out what is it that would limit the performance and scale of a database. And it really came down to like 4 key issues, we thought. One was the CPU cores that are available and to be able to effectively schedule the work for maximized concurrency. Take advantage of the memory. The systems are continually getting higher and higher memory footprints, but ultimately there's a finite, either cost-wise or physically amount of memory per system. Disks are getting faster, but they're obviously not keeping pace with demands, and we see movements now to SSDs and Fusion I/O and whatnot. And these 3 areas, in terms of increased core count, bigger memory footprints, and faster disks, have all been moving along over time. But there was a 4th category that we looked at, with a few exceptions. The science behind the underlying storage engine technology really hasn't advanced that much. Hat tip to Mr. Callahan, of course, on the fractal tree moving it forward. But generally, all of the relational databases and even the non-relational systems that are out there today rely on what I'll call legacy or traditional store and search algorithms, ranging from log files to B+ trees or LSM trees or variations thereof. And they all have their strengths and weaknesses and are generally share a common set of characteristics. One is that they were really designed to perform optimally for a particular workload. So in a very coarse sense, it might be they're read optimized or write optimized, or others may have better index performance than some of the other alternatives are out there. But generally speaking, they were designed to support a kind of a primary use case, and when they're instantiated or put into practice in one of these database engines, their algorithms are relatively rigid in their construction and in their real-time behaviors. So whether that be something that's relatively changeable, like a memory page size, or less so, things like the width of the tree or the size of the depth of the tree, generally the common trait here is that the data structure that is used for this store and search algorithm has its kind of behavioral characteristics tightly coupled with that structure. So they kind of work together in a relatively rigid way. And that kind of fundamental idea, I think, is in principle why we've seen multiple store and search algorithms implemented across these different database technologies. So when we looked at that, we saw an opportunity if we could kind of address a few key questions. One is, is there a way that you can be both write optimized and simultaneously read optimized? Because that's really not been done before. The other is, and we felt is imperative to get to the first goal, is there a way that you can redefine the structures during runtime, so you can, for example, increase or decrease the size of a key space segment or equivalent of a memory page operation, things that allow you to kind of be responsive to the data types that you're dealing with and the workloads that are being presented, and make the algorithms be a little bit more nimble. Also, to kind of decouple it from the constraints of things like memory page sizes and whatnot. And to be able to do this all sort of in a online operational sense, and try and minimize any offline operations, and to do all of this without sacrificing features. So be able to support the full ACID, RDBMS type feature set, and yet be able to jack the performance and scale up substantially. So these were sort of the thoughts that we had entertained as we set forth to try and solve the scale-up problem. The way we approached solving the scale-up problem was taking a step back from the traditional computer science that's been used, and we invented something new called CASI, which is a mouthful, but it's continuous adaptive sequential summarization of information. And it's actually pretty literally descriptive of what we do. But there was a couple of things, at a high level. If you look at the little sort of circle of life there on the upper left of the diagram, really the idea here is that we can observe the data and how it's changing, as well as the work being performed against that. Use this observation to provide predictive analysis to anticipate what is likely to be the next thing we need to do, and to use that prediction to better orchestrate the use of system information. Now, in order to take use of this and really to make it valuable, a couple things we had to do. One is we basically found a way to break the connection to a large extent between the data structure and the algorithm which governs the data structure. So put it in classic terms, like in a B+ tree as an example. At a certain point, the tree gets so far out of balance that you must rebalance it, or at least reorganize portions of that tree. What if you could defer that decision if you knew that there was going to be a more opportune time to do it, or perhaps do it sooner because a less opportune time is coming? Another thing that we did is we said, let's optimize the data structures and how we represent the data and the transactional work in memory from how we represent it on disk. And this would allow us essentially to provide a more optimal data set representation for each of the media that we're talking about. We also took an approach, and there's a bunch of us ex-telecom guys here at the company, and have sort of an embedded systems mindset. So it was sort of a natural act for us to kind of take an approach that's more like an embedded systems level of thinking, and use like a kernel design with scheduling, and we do all of our threading in the user space. It allows us to have better control and get much better throughput by eliminating context switches between the OS, user space and the kernel space. In many cases, in a virtualized environment, that the hypervisor will allow us to kind of run harder because we can stay in our user space a little more cleanly. And then we employed some algorithmic techniques that are based on machine learning concepts to figure out how, based on the data patterns that we're seeing, how the data is changing over time, and the work being performed against that data, to how to essentially schedule resources more effectively. So how we treat data in memory, when we write it to disk, how we group data. These things are all part of this kind of adaptive behavior. That's sort of where the secret sauce to it is. So from a user perspective, what you'll see from a instrumentation point of view is like the CPUs will run hotter, the I/O will have better throughput per IOP, and overall you'll see general goodness in terms of making use of the available system resources. The other thing that we did with our system is we made sure that this sort of observe, predict, and orchestrate is a continuous process. So if the workload shifts over time, even within relatively short periods of time, we can adapt to those changing workloads. It also allows us to say, I might have multiple applications all running on the same database server, and I could have some of them might have write-heavy needs and others may have read-heavy needs, and we can service both of those optimally for the tasks that are related to each of those workloads. And lastly, one of the things that we did was in how we store our data to disk. We don't use a page-based system. We actually write all of our data out in what essentially are append-only files. Think of them as like highly modified log files, somewhat almost like LSM-ish in some regards, that we break the data into blocks that represent chunks of key space. But we embed in these log files a bunch of metadata that allows us to do cool things like know immediately, cardinality, row counts, and other interesting attributes about the data being managed. So as a simple example, if you had a really big table and you did ask for a row count, right, to select count star or select star count, whatever that is, on a big table in MySQL, that could take a long time. For us, it's an instantaneous event because the data is continually maintained and updated.
So, Mike, I actually have some questions on that then. So it sounds like you're saying, so effectively you denormalize some of this metadata as you're writing into this append-only log storage structure. Is that correct?
Yeah, I mean, if you think about what we do is a lot of the information that the query optimizer is going to need to make good choices about query path selection, we maintain that in real time, in constant time. So as we're changing data and dealing with CRUD operations, we're continually updating those stats that are embedded in the index structures as well as the primary sort of clustered index.
Okay, and so I guess my follow-up question on that is, how does that look for kind of locking or contention issues? Is there any sort of kind of painful serialization that might happen in keeping these stats up to date? Because at least with InnoDB, there's a variable specifically to disable stats collection on a periodic basis for that exact reason. Yeah,
no. The short answer is no. In fact, we have some patents on this particular area, and in general, we try to do as much of our work as possible in using what we call lockless algorithms. So we maintain a very high degree of concurrency, but we do so in a way that minimizes our locks. Our lock granularity generally is no worse than a row, so we don't do any table or big key space locks. The idea here is that you want to, like in the case of the stats collection or stats maintenance, that's 100% lockless, and this is again one of the patented areas that we've documented. But I guess if you kind of imagine like how a column store would embed in the column certain metadata that describes like the frequency and the cardinality or uniqueness, data range, support, things along those lines. We've taken that concept, but rather than treating them as monolithic like index structures or columns, which would be expensive to maintain, instead we break the indexes or the primary up into key space blocks that we call segments. And these segments have a couple of key attributes. One is the segments tell you where their adjacent segments are. So in the file on disk, even though it's an appended structure, you don't have to have the whole key space range contiguous. There'll be chunks of segments, and we have pointers forward and backward in the file to kind of move you around. But we calculate all of our metadata on these segments rather than on the monolithic key space. And then we have some interesting techniques that allow us to aggregate that data sort of without imposing any lock costs to the data structures.
So, Phil, the segments sound to me a lot like a column store implementation like InfoBright or InfinityDB would employ. Is that correct to me?
It is. It's a very good way of looking at it. In fact, we refer to our technology as a segmented column store. So rather than treating the columns as these kind of larger monolithic things that, like if you look at Vertica or some of the other systems, when they have to rebuild the columns sometimes because they are monolithic in nature. For us, we've got these smaller chunks of key space, and those. So if I wanted to update, for example, even if it's an insert, an update, or delete, I can do that as an append operation to the disk structure, but that append operation is linked back to the rest of its segment and the segment chain that it's a part of. So it allows us to kind of do the math on smaller units.
So my brief observation on the idea of segments is that it works fine as long as the distribution of data is indeed like hotter in some segments, or distributed unevenly. What do you do with the sorts of data that is completely distributed evenly throughout the segments? How do you index that, or how do you?
It's a good question. So there's a couple of thoughts there. One is, think back to the idea behind these adaptive algorithms. So one of the aspects of the adaptation is that segments can be a variable size. So if I get a block of data that's nice ordered or can be ordered on a write flush to disk, I'll write that segment to be as big as possible given the data that's available. If it's completely random, as you're suggesting, I may initially write that out in relatively small segments, but then we have some background housekeeping tasks that are continually defragmenting the data, and part of that defragmentation process can be segment merging. So again, if you're familiar with an LSM tree, conceptually there's some similarity there. So we can say, hey, get the data to the disk, get the transactions processed as quickly as we can, and then in the background we're able to reorganize or defrag the data in a way that's done out of band or not in line with the transaction. So while we're defragging, you can still be operating on the live data. We handle that use case. So it doesn't impose a cost sort of on the inline workload, but we're continually trying to make the segments bigger and more well-ordered over time. We also, for example...
Would you say, do you think this is like always or off?
It runs as a background test continually. So there's no need to run like an optimized table on Deep. We're continually self-optimizing. We're defragging the table, trying to reorder the data. We're reorganizing the indexes. And just from a data structure point of view, if you looked in a table, if you went to the root data directory for MySQL, you'll see a directory for each of the databases as you would normally see. In that directory, for each table in that database, you'll see multiple files for Deep. We have a sort of a transaction log file, and then like the clustered primary key value file. And then for each of the indexes, they have the separate file. And this allows us to operate on all these files sort of in parallel. And by the way, each of those can have variable segment size depending on what the randomness or the ordering properties of a particular key space may be for an index. And this allows us to kind of move all the indexes forward in parallel and apply appropriate CPU CPU horsepower to different indexes. So some indexes may be more expensive to reorder than others. So we can move them forward in parallel asynchronously, but by applying a different amount of compute resources, memory resources in order to move them all forward together.
So I actually have another question on this too then. I mean, so what you're describing sounds very, very much like setting up an HBase cluster where you have kind of a predefined set of key space, and it's going to be broken into multiple regions across a cluster. I mean, in our case, we're talking about multiple segments on inside of the file system. And so with all these background things going, like that sounds really nice in theory, and as an operator, like, oh, it'd be great if I don't have to run optimized tables and things are just kind of mostly working. But I'm actually more curious about, so how often is it possible for I/O resources and CPU resources to potentially be starved by these background tasks? Like, you say it's adaptive and that they'll kind of back off so you can keep working on the live data, but are they actually cognizant that, if I have a lot of stuff happening on a chunk of data and it just kind of keeps happening and then there's not a quiet point for a while, would that be problematic in the long run?
No, well, I mean, the short answer is, it will not be problematic. We will adaptively hold off some housekeeping tasks, to try and accommodate the inline transactional workload. But at some point, we'll, kind of jump in and do it. And we do it in a sort of a time sharing or a CPU cycle sharing thing. So the idea here is that if I am reordering a segment, the fact that I'm reordering a segment doesn't prevent ongoing work on that segment. So I can kind of throttle it relatively conveniently. And we never get to the point where we have to reorder. If we don't reorder, at some point the system can become fragmented and you'll start to see a performance impact, at least to the extent you have to get data off of disk. But the system never becomes inoperable. Like if you look at traditional, like a B+ tree, at some point, if you don't rebalance the tree, it will not function because you run out of node space. We don't have that problem. On your HBase analogy, I have never heard anybody describe it that way, but I suppose there's some truth to it. The one big thing is we are adaptive in terms of understanding what the key space looks like. So my marketing guy hates it when I say this, but we did a marketing stunt at Percona Live and demonstrated the trillion-row table, right? Now, we can probably agree that there's not a practical use for a trillion-row table in MySQL right now, but we did it to demonstrate that we could take a AutoInc primary key and just insert rows into that table essentially indefinitely. And all we would do is, based on our observation of the rate at which the data was growing, we would start to reorganize or organize prospectively new segments to accommodate a rapidly growing key space. And this allowed us to essentially provide more or less linear performance out. We stopped at, I think it was like 1.1 trillion rows, and we were running on an Amazon EC2 instance, by the way. And it was mostly, like I said, I call it a marketing stunt, but it was really meant more as a mathematical demonstration to show that this concept can scale out to ridiculous scale. And that was using a modified version of IIBench insert index benchmark. So it provides a pretty steady, constant load to the system. So it's a good way to address the question you asked earlier about at some point will defrag, cause a problem or interfere with work. And we can share the data with you guys, but the throughput was very high. Now, granted, it was a simple schema, but I want to say we were inserting something in the order of, it was like 60 million rows per minute. So, you're coming close to 1 million rows a second. It was a simple, I think it was like a 2-column table, of course, but nonetheless, the point here was really to more deal with the size of the key space versus, having a really wide row. Make sense?
Yeah, I have a question. Maybe somewhat ties onto that last one. Let's say that you detect that the workload's changing and you start reorging, but that change was temporary. So let's say that at the end of every day I need to run reports on my LCP data.
Right.
Can you abort, or how do you handle that where you were going to change structures for something that was maybe not useful?
There's a couple of things that we do with our adaptive. So part of it is we look at sort of how hot various parts of the key spaces are, and if I see data that isn't being touched, I'm going to sort of deprioritize the need to defrag or reorder that. If I see another segment that is constantly changing, I may also hold off defragmenting that until it settles down. So it's not consistent with what you're probably used to, where it's sort of it's very black or white. This is much more nimble than that. The other thing is, because we separate out like the indexes from the primary and cluster, each of the index files is individually ordered. So this background process is not just defragging the data, but it's actually defragging all the index files. And the other thing that we do, which is kind of clever, is our secondary indexes have a pointer, entry back into the primary index, but also have a pointer directly to the data on disk. So for us, we can do, a dynamic calculations of the cost of scanning a table, or versus doing a point read directly from the secondary. So in general, what we've tried to do is design a system where the whole background operation never comes at the expense of real-time work, whether that be analytical or transactional. And with respect to the sort of observation, we can accommodate both read and write workloads at the same time, or I might have, we use the example, Monday through Friday is transactions, I run a bunch of reports on weekends. So we'll see the behavior change and adapt to that relatively quickly on like Friday night, let's say use that example. But the data generally has been ordered such that it is both read and write optimized at all times. And it really becomes more of an issue of where I schedule my grouping when I do write to disk, or how I will prefetch when I'm pulling data into cache, is really more on the kind of the observed and predicted behaviors.
So to me, like the idea of like the secondary key holding values both to the primary key and to the data on disk, as well as all this background, defragmentation going on, sounds like a whole lot of I/O, both during writes as well as during normal. So I'm curious about that.
Yeah, great question. So a couple of things there. Because we're an append-only data structure to disk, we don't need to read before write. So it's a kind of interesting exercise. If you were running a insert-only test like IIBench, if you were monitoring IOPS, you'd see close to 0 reads because we don't need to read before you write data, generally speaking. The other thing that we do is the way we go about flushing to disk, to use sort of a conventional term, based on the entropy or the rate of change of data, we'll make decisions about when to write and try and get better groupings. So if you think about how Inno operates, right, they really write everything twice. I write it to the log file, and then I flush it to the IB data files. For us, we don't do that. We have one data structure. So when we write to disk, we're putting it into the equivalent of our IB data structure, and only write out the final state of that data. So you may have a row or a segment that's got a lot of changes going on. We'll end up, not writing each individual change out, but really writing out the final state. And further, because we're not page-based, we have a write amplification of 1 when we actually do put data to disk. So if you were to measure it, it's not uncommon. Like during a I think the II bench is a great example. We probably have a 80% fewer IOPS for a given number of rows created than InnoDB. In a mixed workload, that may fall off to maybe like half as many, but generally you're going to get more bytes written per IOP. Also, because we're append-only structures, we eliminate the vast majority of seeks, which are IOPS. So you end up getting closer to wire speed throughput using our system across most workloads than you would with a B-tree-based solution or an LSM-based solution.
How do you garbage collect then if you're not using page-based and you're using append-only? Surely there are...
Yeah, so great question. So what we do is, as if you picture the data structure on disk, I'm writing out new data to the end of each of these files, and again, you have multiple files that are all moving forward in time. Each segment, one of the statistics that we keep is how fragmented is the segment. So only when a segment gets fragmented enough that it would be cheaper to rewrite that as a new segment, do we rewrite it? And at that point, we'll also make a determination, hey, does it make sense to merge multiple segments into a common segment, which again will further optimize the write throughput on that. As a side note, the way we do compression is very similar. We'll go in, when we do a transaction, we write the initial data is written out as non-compressed, but then as we come along and do the housekeeping or the garbage collection, as you refer to it, at that point when we rewrite the segment is when we'll write the data out as in a compressed form, if it makes sense to. We also have some smart algorithms that basically say, hey, I compressed this and it didn't compress at all. Let's say it was like a video object or something. So stop trying for a while. When we get data that is fragmented, what we do is we rewrite it, and then we get these files that essentially have nothing in them. They're old data. We'll purge that. We'll delete that file or that section of file when it no longer has useful or current data in it. So it's kind of think of it as a moving window through time. As the log files grows, the older, the lower numbered rows end up becoming archived data, and then we can either delete those or we can mark them as archive and keep them around. But one of the interesting side effects of this approach is our database, we never update in place, so there's, I guess, definition, remove some opportunity for data corruption. But more importantly, we can roll back to any point in time. So the error recovery for us is a very natural effectiveness. And secondly, and we haven't productized this yet, but in theory, we could have let's call it like a time machine type application where you could rewind the database to any point in time in the past, disk space allowing for it, of course, because the data state at any point in time, it always exists until you choose to delete it.
To some extent, this sounds a lot like PBXT. Are you familiar with this storage engine?
Not really. That's one that I don't run across often, so I'm not familiar. I can tell you that generally the things that are unique about or worth mentioning with us, this is a fully ACID compliant transactional engine. It does read and write optimizations. It supports the full MySQL features. So we do different isolation levels. We can hold a lot of storylines and view perspectives very efficiently, by the way. So unfortunately, no, I'm not familiar with that particular engine.
Yeah. So that was a one-man gig, Paul Magula, and it kind of died like 5 years ago, but as he published it, it was also an append-only, garbage collected. Sounds quite similar, but I'm not familiar with all the details, of course. But it sounds very similar to what you're describing here. And the day he published it, I remember Mark Callahan was benchmarking both InnoDB and PBXT and was highly impressed with the PBXT performance. So I'm just curious if there's any connection.
There may be no relation. What they say in the movie is right. Any similarity between real people is a coincidence. The idea here, and I've seen this before, as we go through the description of what we do. I've heard there's in fact there was an architect from AT&T, and he said, "I've heard a lot of what you're saying, but never together at the same time." So people have done garbage collected log files. People have done some other non-memory map operations. Some of the indexing, column store attributes. So it really is sort of the bringing together of these things in the way we have it. I think really is sort of what brings the value. And I am sensitive to time here, and I just want to kind of move it along. But please keep asking questions. So what do? We built this cool new technology. We delivered it as a storage engine for MySQL, and we did that for a lot of obvious reasons. MySQL architecture is natural for supporting multiple storage engines. It's the most feature-rich platform, or one of the most feature-rich, full-function relational database management systems. So kind of prove the technology can work in the worst or most difficult use case. But it is our intention over time to make the Deep Engine technology available under other database heads. But right now the company is fully focused around the MySQL world and its forks. We support both MySQL and Percona today, for example. And it's designed to plug in right next to the existing storage engine. It was designed to be a alternative to the InnoDB or XTreeDB in the case of Percona storage engine, and provide sort of a application compatible, schema compatible alternative engine. And relatively small. It's a you download. It's a 10 meg plugin. It installs using standard Linux package tools and shows up as a new engine under the hood. From a data, just kind of some benchmark stuff, and I won't kill you with a million slides here, but I just want to kind of illustrate the two principal cases. One is ingestion or insert, write heavy workloads. So what we did here is essentially use the IIBench tool with the insert only mode with the secondary indexes turned on. And we created a table of 100 million rows. You can see the kind of most of the scheme. I think I left the table statement off the bottom, but to the right. And then once that was created, we also ran some queries against it. Again, very simplistic schema here, but the idea was to see, can you handle an ingestion rate when you're doing a reasonable amount of indexing, which is getting more and more common these days. And the results are pretty interesting. So this was run on a decent-sized bare metal machine. It was a 32 CPU core machine, 8 gig cache, running on a 4 drive wide HDD RAID. InnoDB is tuned to make it perform well, so we're not trying to run it like with a my.small config or something like that. So this was running a pair of 256 meg log files. It's running with ample, the same buffer size as Deep. So we tried to keep everything the same. I think this case we were running, it was like ODirect was the flush mode, and these are all full durable numbers. And you can kind of see in the chart, our insert rate is, substantially faster than InnoDB, where we were able to create 100 million rows in about 525 seconds. It took InnoDB something in the order of 9,000 seconds to do the same test. The queries maybe need a little bit of explanation, and what we tried to do there is we did two kinds of queries. We did what I call an index query. So we basically just said, go and select something from a table where that something is in an indexed column. So essentially, I'm just pulling the secondary key value out, and you can see we're about a little more than 2x as fast there. And then the next two columns, the rightmost two, were basically doing what we call a point read. So this basically said, select star where a particular secondary index criteria is met. So you actually have to pull the whole row. And so for both the index only and a point read or a row read, you can see that we're north of a 2x faster read performance. So this is, like I said, this is basically using IIBench is the behind-the-scenes table creator and running these queries essentially ad hoc from the command line. The cold start is essentially, as you probably well know, is bring the machine up, don't do anything except run the query so you can see what the cost is of getting the data in from disk, and that was really what the purpose of those measurements were. To look at it from a read-heavy workload, we also ran a DBT3 benchmark, and this is running across scale factor.
Did Mike just...
You guys lose me? Hello? You hear me? I see Tim giving me a thumbs up.
Yeah, so good.
Okay. So you guys are probably familiar with DBT3. It's an analytic benchmark. It uses the DBT2 database as the target database to run queries against. And basically what I did here is run from scale factor 1 to scale factor 5, varying the scale factors, varying the cache sizes across a number of different configs. And on average, across these runs, we were just shy of 2x faster than InnoDB. This data, this chart, was done against our last release, release 2.1. We just released version 3.2, and I don't have all the data yet, but at least the first 2 columns on this picture, we bumped north of 2x, so we've seen an uptick in read performance, and that's because we did put some new optimizations in our adaptive logic, which is one of the cool things about the architecture. We can evolve sort of the adaptive algorithms to take advantage of new things we learn. But again, the idea here is that it's also got good read performance. The third scenario is more a full stack. Okay, so benchmarks are one thing, but they're all synthetic. What about a real-world use case? And unfortunately, I'm under NDA, so I can't disclose the real customer here. But this is a pretty big Drupal site, e-commerce type use case. And what they've got is a pair of Apache web servers load balanced in Amazon, sitting in front of a database server. They're running Percona 5524. And what we did here is we basically took a production machine, we cloned it into our system, and then ran a series of JMeter clients to simulate end user traffic. And we did this. The footnote here is, if you notice, we're running the InnoDB. Their production was running on a C3 4x large Amazon EC2 instance. We ran deep on a C3 2x large, so it's the next size down, because we wanted to demonstrate that we could generate or extract the stranded resources, which comes back to the questions about garbage collection, what the overhead is. The punchline here is we were able to load the data 4x faster. The size on disk was about half as big. The queries were faster, and the end user page load experience was better. And we did it on a machine that cost half as much, right? So that's the punchline. The details are shouldn't be surprising. The load, we basically did a MySQL dump of the production data system. We moved that over to two test machine suites in the Amazon cloud. We loaded both of those dump files into the respective test machines. We loaded, and we loaded over 4,000 seconds. Took about 18,000 seconds, and you can see the size on disk was about half as big for deep. And again, this is because we do our compression, because we're not doing it inline. We're not limited to compression, limited to a page size worth of data. I can compress on segments, or if I'm merging segments, multiple segments, so I get a much bigger data space to compress, yielding better ratios. For the queries, we actually did. We took it was a Percona, the Query Digest utility, and captured, I think it was 10 hours worth of traffic on the system, and isolated out their top offenders, if you will. So we took the top eight queries, which represented about 70% of the digest query log, and what we did was we kind of did a sort of A/B comparison. What was the hot and cold response on those for us versus what it was for Inno? So if you look at the simple average, it basically says weight all the queries the same. How much faster are we cold, and how much faster are we hot? The weighted average basically factors in the percentage that each query was run and tries to apply a weight to the frequency that a given query was hit. And you can see, while cold got pulled down a little bit, the hot got pulled up a little bit. But the point here is this is actual real-world, full-stack, mixed workload using Drupal. The last punchline, this is probably an eye test for you guys, and I apologize, but the customer was monitoring this through New Relic to measure the end-user performance experience. And what you'll find here is that we essentially cut the page load time or response time in half. We doubled the transactional throughput of the system and raised the app score from a 0.12 to a 0.45. So about almost a 4x improvement in app score. And this, again, is looking at all layers. So this is the PHP, Apache. I think there's a varnish layer here. So, just changing the database, no application changes, no new indexes being created. They were able to drop this in and see this kind of performance improvement on the product, which, again, I think gives you a better sense, perhaps, of what we'll see in a mixed workload environment. So, that's sort of.
I was going to ask a question. If you go back to the last slide, why there's a huge variation of a bit of a sawtooth pattern under the web transaction response time using Deep Engine? Is that potentially because of garbage collection taking some resources, or was that actually looked into at all?
Yeah, it's a good question. No, but what you have to bear in mind is that because the database is running faster, the Apache servers are running more. So if you look at the blue section on the bottom, you can see the sawtooth actually starts there.
I see. So
it sort of gets amplified through the layers, for lack of a better way of describing it. But if you look at the stats in terms of like average transaction latencies, our averages are. I've never seen a case where our average is higher than any workload. And probably more importantly, our worst case latency, like if you look at a Sysbench and look at like they do like a min-max average, our max is generally an order of magnitude smaller than an InnoDB max. Because you have to bear in mind, and you guys all probably have seen this in your environments, right? When that log file, if that has to flush, that creates a big performance drop. We don't have the idea of these write-ahead logs that have to get flushed, so our performance tends to be much more stable indefinitely. So we don't have these sort of periodic drops. And garbage collection is really a relatively innocuous task. In fact, I would suspect if you guys looked at most of your MySQL production servers and you would have monitored the CPU core utilization on those machines, more often than not, there's a lot of idle cycles. And we essentially try and exploit that to the best we're able.
So I can probably see this being part of a benchmark, but this brings me to my other question: is how much of configuration for what Deep Engine is actually doing, especially when deciding like how many times how often it does this garbage collection, like what percentage of I/O is allowed to have, any sort of configuration there. How much of that is dynamic, and how much of that work is visible through statistics that can be easily thrown into a graphite or something? Yep. Because I can imagine, regardless of whether this sawtooth pattern is which part of the stack, an operations engineer or a DBA is going to want to make this look more, even if it goes a little lower, but we would like it more predictable than that. And so people will probably want to have an easy way to tool around it to actually tune it without downtime.
Yeah, great questions there. So our ideal world is you install it and you configure nothing, at least with respect to Deep. So it'll discover the number of CPU cores, available memory, it'll manage all of that dynamically, how many threads it should use, and when it runs garbage collection or reorganizes segments or whatever it may be doing. You do have the ability, so if you do to show variables like Deep, you're going to see about, I don't know, probably 20 or so variables will show up on the list. Those are all able to be overridden. So if you want, we do a lot for benchmarks, for example. I want to make sure that my memory that I use for my cache is the same as Inno. So I'll override our memory manager to say, never let the cache get bigger than whatever the value happens to be. Similarly, our default behavior is to run in fully durable mode, which is like flush it text commit equals 1 in Inno speak. But if you're running in like a value of 0 or 2 for Inno, you can have the same sort of knobs you can switch for us. So the a number of threads available for garbage collection and indexing is also overrideable. So, but generally, all of the knobs are overrideable. We generally think you don't need to do it, but they are there. In terms of statistical information, today we dump all of our information out, including all of the housekeeping related things. So like when we're reorganizing data, when we're rebuilding an index, when we're purging memory. All of that is logged into the MySQL error log, or whatever the default log you set up is. And that level of debug or logging can be changed on the fly, at runtime using the set global commands. And they're all in a standard syntax, if you will, or parsing format for us. So if you wanted to have a utility that was tailing the log file and extracting deep things to plot it out, it certainly can be done. We also support the ability to mask out certain event types. So the logging system is very extensible, very flexible. At the present time, we have a base integration with the information schema that you'd expect. So like all of our table stats and stuff are there. And today we don't do anything specific with the performance schema for Deep, although most of that data is available in the log file. Our intention is in the future releases to make that available in addition to the log file, to put some of that into the performance schema, because I think that's sort of, people tend to expect to see it there.
I got a few operational questions. So first question from one of our readers. Is it possible to control, to modify behavior, to declare behavior for, the cleanup, defragmentation, the behavior analysis, etc.? Can you provide some hints to the system?
Some of the parameters are adjustable, like, for example, how often we do checkpoints for data recovery is configurable, a number of threads available for the garbage cleaning is there, the fragmentation percentages that you need, the thresholds you set before the defrag and garbage collection will kick in are configurable. Again, our experience thus far is that those are relatively self-governing and reliable, but the information in terms of when we're doing what and what percentages we're triggered at are available in the log file, and you have the ability to configure those either in the standard my.conf type configuration files, or from a command line launch if you don't use the my.conf, or from a runtime set command.
So another two questions. One is just curiosity. Did you manage to break the barrier of one core per query? That's the first question. And the second is how well does it play with MySQL applications, statement-based, role-based, etc.?
I got the first half of that question. I missed the second part. It kind of dropped out.
Oh, okay. So the first question was, were you able to break the barrier of a single core per query? And the second one was, how well does it play with MySQL applications, statement-based, role-based, etc.?
Okay, great. So the first half is, unfortunately, we are not doing anything on the head. So as you are probably aware, the query optimizer will come down and ask for cost information from us. We respond with that costing. To the extent that the retrieval in response to the GET requests that we're getting from the query can be parallelized within the storage engine, we absolutely will do that. But we don't solve the problem of sort of the multi-threading of queries at the MySQL level. But within the storage engine, to the extent that we can parallelize the work we do. The second question was with respect to replication. We support both statement and row. We're compatible with MySQL as well as Tungsten in the various configurations. Again, we don't change any behavior there. So if you're running 5.5, you're single-threaded per whatever that is per database. If you're in 5.6, you get threads per table, and as that evolves over time, we'll evolve with it. But right now, we don't really bring anything that was overly magical to the replication. We do see in a heavy workload environment that our replication lag is shorter generally than we're not talking about like orders of magnitude, but maybe like 20 to 40% under load on a system that's idle. There's going to be a wash because it's a single thread. So we're both constrained in terms of the work being fed to us. One other point, though, on the subject of replication that's worth mentioning that may not be obvious is because all of our files are written as append-only data structures, it's possible to do things like backups and hot standbys using simple file system techniques like rsync, because the rsync, you can receive rsync from the target, the source directory, to a target directory, and at all points in time, the target directory is always a valid database state. So unlike InnoDB, which has an update in place model, and you can end up, if you tried to rsync or copy an IB data file, the destination at certain points in time can be a version, a format that is never valid. It's never been a valid state. For us, the target is always a valid state. So it provides us some unique opportunities to do things like real-time streaming backups or continuous backups, LVM snapshotting, because you're essentially only copying the delta changes over time, and it allows us to operate the file system level. So while that doesn't replace replication in all cases, for those of you that might be looking at replication, a means of providing a current backup with failover, our file system-based approach may provide an alternative to solve that particular problem with replication.
So I actually had a small question on backups because that was something I was going to ask about. I mean, you're saying so you can use these file system tools. I mean, so do you still have to do a flush table with read lock? Like, is there some sort of centralized LSN number that needs to be tracked somehow? Because it sounds like there's a lot of different files for indexes, for the primary key, for the actual data. Like, there's a lot of things all over the place. It seems like.
Yeah. So there's if you think of it from the files perspective, you have I'll call it the log file, which is essentially a transactional log. Then you have your primary key with its associated row data, and then you have all of these indexing files. The rsync is only copying over the deltas. At the same time, as part of this sort of background garbage collection process, we're writing checkpoints out into the file. So let's say that you were doing an rsync and the target machine, one of the index files, didn't get the last chunk through, right? Well, if you brought up a database on that target, what we would do is we'd go across all the files and say, hey, what's the last checkpoint you guys all agree on? Start there and then build out the rest of the play it forward, if you will, from there. So if I have an index that was missing records, we would just create them on the fly. In fact, you could go on the target machine, you could delete all the index files, start up the database, we'd say, hey, the indexes are missing, let's go build new ones. Obviously, that could be a lengthy process, and we rely on the checkpointing to kind of give us a head start. So you set up a point in time where all of the data structures agree that the world is good at this point in time, and the discrepancy is after this point. So let's recover only that point forward. So you don't I don't know if that answers your question, but we essentially can deal with the discontinuities, if you will. You could run the risk, I suppose, that if the primary system was in the middle of just completed a commit, and the rsync hadn't copied that delta, and the primary machine went down, you would lose that transaction potentially.
Yeah, I think it's more from an operational perspective of I have a file, a directory where all the data lives. If I just rsync that over while the server's running to a new machine, and I boot up MySQL on this new machine that I rsync this data to, I mean, would it come up immediately? Is there maybe a couple minutes to do some replay? That's more what I was curious about.
Yeah, so it depends. So if you, and obviously you want to shut the rsync off before you started the new machine up, right? So that you don't want the primary guy changing his data while he's live. But when that guy comes up, he's going to go down and check out the files and says, hey, are you guys all in a good state? And if they're in a good state, it comes up immediately. Only if there's a discrepancy amongst the indexes in the primary that will go into a recovery mode. And the recovery mode is relatively, certainly comparatively speaking, fast. So you can recover a very large table in seconds, depending how far it is from the last checkpoint. And typically, we're checkpointing, I want to say it's like every 600 or 900 seconds, something in that range. And that'll vary slightly depending on the load, and we'll delay it. And that is configurable. But worst case, when you brought that far end, the target machine up, he should have no more than 600 to 900 seconds worth of replay time to play if the file system, if it didn't copy cleanly. Does that make more sense?
Okay, we got about 5 minutes left, so I think.
Sorry, I didn't even take that long.
No, everyone had a lot of questions, so I figured, for everyone who's still here on the call, other questions, we might as well just, spend another 2 or 3 minutes asking questions that we can wrap up for the week. Is everyone all questioned out?
I'll throw it out there. Go get a developer copy. It's from the website and try it firsthand. It's the install takes literally less than a minute, and the only schema change really is alter table engine equals deep, or whatever your favorite mechanism moving data around is. But it's designed to be as low friction. We don't do our own distro. It's a plugin for existing MySQL. I think I had the screen up a little while ago. CentOS, Ubuntu. We're currently GA on 5.5, both for Kona and MySQL, and we're beta right now on our 5.6 release. You can download a copy. The developer license is free, unrestricted, no time bomb, no limitations, so you get a full feature version of the product. And then the enterprise license is relatively inexpensive, should you choose to go down that path. But we're really trying to let people try it for themselves, because it's one thing for me to sit here and throw slides at you, make all these bold claims, but we stand behind the product. We're excited about it, and folks like yourselves will be able to put it through the paces better and realistically than we can.
Okay. Yeah. So I guess just last chance. Any other questions? Tim, Sylvia, Shlomi, Phil, Morgan, anything? Tim, you've been very quiet this whole call. I just wondered if you had anything that you wanted to say.
No, I'm looking to get more. I've had a little bit of hands-on time with it, looking to get more. You know me, I'm really curious about performance and compression and other aspects of it. So, be nice to see it an open source version, Mike.
Hear that once in a while.
Okay. Well, then I guess we can probably call it a wrap for this week, unless, again, last chance for questions. Phil, looks like you unmuted your mic. I'm not sure.
Well, I just had one question. How, when the 5.6 is beta, everything we run is 5.6. How beta is beta? Like, do you have a list of known issues?
Yeah, the short version is it's the 5.6 feature set running under 5.6. So we haven't released some of the optimizer enhancements, like index condition push down. We haven't released the enhanced precision time values. So if you look, basically it's 5.5 features running under 5.6. It's rock solid. It's the new, what's new in 5.6 hasn't been released yet.
Okay, so it probably wouldn't be an issue throwing it on and still comparing it to the NMD.
No, we routinely run, in the data that you saw earlier, is basically running Sysbench, IIBench, DBT2, DBT3, running 5.6 deep.
Okay.
None of those products require the 5.6, like global transaction IDs or anything along those lines.
Right.
But the core functionality is rock solid.
Okay.
Okay, cool. All right, well, Mike, thanks so much for coming on the call and fielding all the questions, talking about the products. And I think we can call it a wrap for this week. And so next time we'll be picking up on the other topics we had for today, talking about automation and expectations of a DBA. So thanks very much, everyone who participated today. Thanks, folks who are streaming and ask questions offline. And we'll see y'all in 2 weeks.
Thanks. See you guys.
Thank you.
On.